Okay, yeah. So this is the third problem on the 2017 Stat 110 Live Solve. Um, as always, do the problem first, get a feel for the problem, and then return to watch this video. Hopefully it's a good time. Yeah, let's just get started. So I'll just read the question. The sociologist Elizabeth Wrigley Field posed the following puzzle. American fertility fluctuated dramatically in the decades surrounding the Second World War. Parents created the smallest families during the Great Depression and the largest families during the post-war baby boom. Yet children born during the Great Depression came from larger families than those born during the baby boom. How can this be? So I guess this question is going to go towards answering this how can this be question. So part A, for a particular era, let n sub k be the number of American families with exactly k children, and for each k greater than or equal to 0. Assume for simplicity that American history has cleanly been separated into eras where each era has a well-defined set of families and each family has a well-defined set of children. We are ignoring the fact that a particular family size may change over time, that children grow up, etc. For each j greater than or equal to 0, let m sub j, so this is just a big notation chunk, m sub j equal the summation from k equals 0 to infinity, k to the j times n sub k. So n sub k, this is number of families, and k is like kids, kid number with kid number k. Okay, so the question is, for a family selected randomly in that era, with all families being equally likely, find the expected number of children in the family. Express your answer only in terms of m sub j. So, okay, so we're going to want some sort of like sum of total number of families, and then what each family saw. Okay, so each family, so there's going to be like, yeah, so let's call x be number children in randomly selected family. Okay, so there's going to be n sub k fams that see k children. Is sort of the heuristic that we're going to want to take on. So that means on the top, we're going to have like 0 plus 0 plus dot 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 plus 0, and then this is going to happen n to the 0 times, and then 1 plus dot 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 plus 1. This happens n to the 1 time plus dot dot dot, just like the same thing over and over. So that's going to be the number of children that like each family sees. And then for each one of those, there's a probability, like it's a randomly selected family. So there's going to be like just, we want to sum over the total number of families, which is the sum of all the NKs. So to kind of summarize that, I'm going to like write up here, that's going to be in the denominator, sum from k equals 0 to infinity of nk. And then here we have like 0 times n0, 1 times n1, and then 2 times n2, and that's going to go on forever. And so that's going to be the sum from k equals 0 to infinity of k times nk. And if we use this mj notation, that's going to be j equals 1 for the top, so m1, and then j equals 0 for the bottom, so m0. So this is going to be our solution to part A. Okay, so for part B, now for a child selected randomly in that era with all children being equally likely, find the expected number of children in the child's family. Okay, so this time, like if you look at this thing on the top here, this is actually the number of children in the family. Well, I guess not there, like here. Like there's going to be All right, a number of children total. So that's like 0, 0, 0, 0. And then there's n1 that's like 1, 1, 1, 1, and then plus 2, 2, 2, 2, 2. So the total number of children, and we're doing child selected randomly, so it's going to be 1 over number of children total, which is 1 over sum k equals 0 to an infinity k n k. And let's figure out like what these children see. So there's going to be n sub 0 children that again see, let's see. So each child is going to see themselves, find the number of children and child. So they're going to see k people in their family. So there's going to be, yeah. So for each one of these like children in here, we have like, well, we have some, there's not going to be any children here to count, but here, these 1 children, they're each going to see 1 person. These like 2, every one of these 2 children is going to see 2 people. So there's going to be n sub 1 kids who see 1 person. There's going to be n sub 2 times 2 kids, because each family of n sub 2 has 2 children. These are each going to see 2 people. N sub 3, these are each going to see 3 people. So this is going to be something like k squared, or like, I guess it's going to be like k and k children see k people. So that's going to be k squared n k. So that's what we're going to sum up on the numerator. So for the numerator, we're going to have, I'll just write it here, sum k equals 0 to infinity of k squared n k. And using the MJ notation, that's m2 over m1. Okay, so for the last part, give an intuitive explanation in words for which of the answers A and B is larger, or whether they're equal. So this is like kind of fun, because like this is, we've seen this problem before. This is very similar to the student I, Dean's I, like average problem on a P set somewhere. And the analogy is that like part A is going to be like the dean's eye view, because they're just choosing families. Like, let's call a family a class, and the number of kids is the number of students in that class. So this is like part A, the family's eye point of view, and student's eye is part B. So I would say like intuitively that, well, yeah, I would say intuitively like the student's eye is going to be larger. Yeah. And that's just because there's going to be like a ton of kids like this, yeah, there's just going to be a lot of kids in these large families that see a lot of people, and maybe very few kids in small families that see very few people. Yeah, so that's my intuitive thing, I guess. Like, lots of kids in large families see lots of people. I'm gonna check what I actually wrote on my real final. So on my real final, I said, this is similar to the student's eye versus Dean's eye class averages. Nice. Part A represents the average from the parents' point of view, and part B represents average family size from the children's point of view. Okay, so exactly what I thought just here. Okay, and now let's figure out how this relates to Wrigley Field puzzle. So I'll put this away and try to figure out what I might have said. So like the Wrigley Field puzzle is saying like there's like large people born during the Great Depression came from larger families than people born in the baby boom. And I think that's probably because in the baby boom, there's not that many kids. There's just like smaller families. So they all see really small families in general. Wait, does that even make sense? I guess like, okay, so children born during the Great Depression came from larger families than those born during. Okay, so the second line, parents created the smallest families during the Greatest Depression, that kind of talks about like the parents' point of view, like the average family size. So the average family size in the Great Depression was smaller than that for the baby boom. However, I guess what it's saying in this last line is that the children's point of view is not is actually larger in the part B version. Yeah, is larger in the Great Depression than the baby boom. And it's just saying like it sounds like a contradiction because they should be the same since they're both averages, but we just saw that these are averages from different like points of view. So one's the dean's eye and one's the student's eye. Okay, so see what I wrote. In the Great Depression, there could be many families with no/few children and some amount of very, very large families. And so the children and the large families will compose the majority of the average, and it'll push the average above the child's eye than in a more balanced era like the baby boom. So I was saying that in the Great Depression, maybe there's like a lot of really tiny families, but then maybe there's like one gigantic family. Okay, maybe a few very large families. And because there's like overall, it will seem like there's not that many like families, or there's just not that many like families in general. So the average family size will be smaller. But the number of children that see these large families versus like the families with like just no children, that's going to push up the child's eye point of view. And I'm saying that like the baby boom era might have been a little more balanced. There's going to be families like from not just like focused on the very small families. Yeah, okay, so hopefully that intuitive explanation made sense. And that's my solution for problem 3. And I guess I'll see you guys for the other problems later. Good luck studying.